Hi, my name is Hazem Gaber, and today we're going to be talking about circuit breakers. So, in the NFPA, or not NFPA, but in the National Electric Code, or in an engineered specification, we don't say circuit breaker, we say overcurrent protection device, which is what a circuit breaker is. But in this case, we're just going to say breaker. So, on the right is a breaker, and this is a 3-pole breaker. So this is quite an old breaker for like an MDP or a CDP, and it's in the off position. You can see the handle, and then at the top we've got 3 contacts. So breakers are found in electrical panels, and then now here we've got what's called a disconnect switch. So this is a fuse disconnect. It's also a 3-pole. So if we look here, this has got blades, and on the right here we've got a switch, and it's in the off position. So you can see on the dial it's got off and it's got on. So these electrical wires go to supply. Is this a supply side, or can't tell? But basically, this system, if we go back to um, if we go back to our breaker, so we're going to learn more about this, but basically our breaker is designed to disconnect the power. So power is coming in from power comes in from the panel. This is normally mounted so that this bottom part faces the center of the panel, and this part faces the outside. So power is coming into the breaker from the panel, and then it's coming out of these contacts, which have wires typically, and these go to our equipment. So if we got too much current flowing through the breaker shuts and breaks the contact between the 2 sides, and then we don't have power anymore. Now, in a disconnect switch, this one's fused, which means it's got fuses. So if we got too much power going through, instead of actually tripping or closing the switch, what happens is the fuse melts and the power, and so there's no more power flowing through the fuse, and so that physically cuts it off. But the only way to get the power back in is to put a new fuse in. So, but at the same time, we can manually turn the switch off by turning the switch into the off position. So it's got two different safety mechanisms here. Now fuse disconnects are less popular than breakers, because if a breaker trips, you just turn it back on. But if a fuse melts, then you need an electrician to come change the fuse. Now, sometimes you will see a diagram, or it'll say more than one live circuit. So this could be any kind of device or panel, and the reason is in industrial equipment and some commercial equipment we can have 600 volts for motors, or we can have 347 volts for lighting. We can have 208 volts for motors. We can have 120 volts for equipment or controls. We can have 24 volts for controls. 24 volts sometimes isn't dangerous, but still you want to be careful. So before you work on something, you want to check that you've disconnected all the different sources of voltage, and that you're electrically safe. Now, as I was talking earlier about lockouts, so this is called a lockout hasp, and this one lets 6 different people, because you can't put 6 locks on a switch. It's not going to fit. But what you can do is you can turn the switch off, and then this thing opens like it's pivots on this rivet, and so you can lock the switch with this in the circle here, and then each person can put a padlock in one of the holes, and then this thing will not open unless all 6 locks are removed, or as many locks as are on here. But this gives us the ability for 6 people to work on the equipment and lock it out. Now, on top of that, you need to have a warning tag, so you can put the warning tag on the physical equipment. That way, if somebody comes up to the equipment and says, "Why isn't this thing on?" then they say, "Oh, it's not on because somebody's working on it." So then they won't go to the breaker and try to turn it on, because people are dumb. So they'll see this thing, and if it's not on, or it's not on really well, try to somehow get this equipment turned on, or even cut the tag off. So why is electricity so bad? Because we can't see electrical current, we can't hear it. Well, you can if it's really bad, but typically you can't hear it, you can't taste it. So that's why we want to stay 7 meters from electrical lines if possible. An arc flash can reach 20,000 degrees, and so that in an enclosure it will heat the air to the point where it can blow the door right off. So now sometimes you can touch a live power line and not get hurt, but that depends on the situation. So the more resistance you have, the less current will flow, and so your skin has a resistance of 100,000 ohms when it's dry, but only 1,000 when it's wet. So the wet skin is much easier to electrocute than dry skin. And then your brain only has a resistance of 100 ohms, so ear to ear you have only 100 ohms of resistance. So you can really cook your brain if you're in the wrong spot. Now let's take a look here at how much current can kill you. And we're only talking milliamps here. So a single between a single milliamp you can't feel it, but around 8 milliamps is like a static shock, like static electricity. And then between 8 and 15 is painful, but we won't lose control. By 15 milliamps, if you touch it, you can't let go of it because your muscles will freeze and it'll lock on and it'll hurt. And then between 20 and 75, you'll start to have breathing difficulties. And then over 100, you'll have ventricular fibrillation of your heart, which also known as VFib. So that'll kill you. You'll be dead within 4 minutes, unless someone has a defibrillator. Then they can try and. So what happens is over 100 milliamps. If it passes through your heart, doesn't always, but if it does, it'll disrupt the electrical rhythm of your heart, and your heart will start beating randomly, and it won't be able to pump blood correctly. And the only way to fix it is to put a defibrillator on you and restart it. Give it a really big shock so that it returns to its normal rhythm. But if they don't do that within 4 minutes, you're better off dead because you'll just become a vegetable. And then over 200, you'll have severe burns on top of that. So you'll be dead and it'll hurt. So in many cases, actually, what they found was between 100 and 200 milliamps is really bad. It will cause the VFib, but over 200 actually won't cause VFib because the current is so strong that it will shut your heart off completely, and it won't. you won't go into VFib, but they can give you CPR and in many cases restart your heart. So if you see somebody, in a lot of these cases, if they touch a voltage or a current that's really high, they cannot let go of it because their muscles freeze. So you will want to not touch them because then you'll end up the same. You want to get something insulated like a fiberglass or a piece of wood and try to hit them away from the current before you do anything. So how do we stop people from getting shocked? Well, we can't, but there's a number of ways. So first of all, uh, everybody that's working should be qualified, and whenever, if we have to, we should try to not work on live circuits wherever possible. But if you absolutely, so if you can shut off the power, but if you can't, then always assume the circuit's live, and always have at least two people working together. That way, if one of them gets hurt, the other one can get help for them. And then avoid wearing jewelry. Always stand to the side of a breaker when opening it. Make sure you close the switch completely and in a firm manner. That reduces the risk of an arc flash. You have a Type C fire extinguisher. Use a ladder made of wood or fiberglass because it's not conductive. You put rubber blankets on adjacent wires and metal when you're working on a live circuit, and that reduces the risk of electricity jumping from the wire you're working on to another close by wire. You can use a Megger meter to check for uh, cuts to the wire or like leaks in the insulation. And you can use electrical proof gloves. They're like rubber gloves, and you can wear them. You should wear them when you're working on a live circuit. But they do get damaged easily, so you want to test them every day to make sure that they're airtight, and then you want to use a leather protector over the rubber gloves so they don't get torn because they're very expensive and you can't um, once they're torn they're ruined. Now, so if somebody is still gonna get shocked, because people get shocked, so don't touch them. If they do get shocked, try to shut the power off, and if you can't and you want to pull them, you want to hit them with something insulated so you can keep them away from the power source, and then have them lie down. So you don't want them to fall into shock or get like a really bad back or neck injury, and then call 911 and start CPR. If you've got a defibrillator in there, you'll want to use it. Now, even if they're not in VFib, you can bring the defibrillator and just check, because the AEDs that are on site now, they'll check the person's heart rhythm and they'll only shock them if there's a shockable rhythm. So if their heart's beating fine, or if it's not beating at all, it won't deliver a shock. And then eliminate the danger. So whatever electrocuted that person, you will want to fix safely, and then make a report. Now, of course, we can prevent every accident is preventable, especially when we have a nice clean job site, and look out for hazards. So if you can't stop a hazard or you can't get rid of it right away, then you want to put up a barrier. So you might have, let's say, a hole in the ground. You can't get rid of the hole, but you can put a railing around the hole. And again, make sure you've got your safety glasses, gloves, and the hot stick. Any questions, please post a comment. Thank you.